This morning we are going to see the concepts of block diagrams and the concepts of bond graphs, and we are going to compare them side by side, and that way we'll get this concept correctly. So why don't we put on this left hand side, I am going to put the block diagram, and on the right hand side I'm going to put the bond graph. Okay. I think we could start with just about any element, but I'm just thinking that we could just pick one, basically a random. I'm just going to pick a resistor on an electrical system. You know, you have a voltage across in here, and then this is the element, and of course you have a current that circulates through it, you know, I like this. So if you let's recognize the the law that this element actually works under. Remember that is Ohm's law, right? So you could write it like this. I am just gonna use a couple of ways that we know this law. Remember that they tell you to remember the word bear, then you know that voltage equals to current times resistor, right? This is the, okay. Now let's begin looking at this thing as if we have an equation in here that how's the computer computes this? You have to know I to know V, right? Or you could say that I is V divided by R. Nevertheless, whatever it's on the left hand side is the result of the computation, right? Or you may say, why don't we say this result, and then this would be you could say the input or the action. Let's call it action, or also call it input. Yeah? So if this is the action on this side, you could say this is the reaction on this side, the result. Okay, say result. This is an important thinking that we need to represent this. Isn't it true that if we represent this in a block diagram, the way it works is you put first the input, right? And then later on the output. So if we represent this equation in block diagram form, because block diagrams are the graphical representation of equations. So it follows that what you need to do is to say this is I, and I put it through a block that does a certain operation with I, in this case multiplies with R, and out of it comes V, right? I think is, so this I think this is very obvious here. You see this is input, and this one is the output. This is of course the Simulink term. This is how Simulink does it. You could represent it in a general term for any system, or for any element for that matter, this way. You can say this is the input, and this is the output over here, and this is the element. Let's call it, we could even say a system, or just call it element. Yeah? All right? So these representations are equivalent. But keep in mind that the representation of this is actually equivalent to the representation of the equation that V is equal to I times R, right? Okay. But you see, I also had it this way. It follows that I could, so this is, let's call it option number 1. Okay, option number 1, I is the input, B is the output. But option number 2, in this case, B is the input, and I is the output. So how do we actually represent that? We have in here the equation that says that I is equal to V divided by R, like that. So isn't it true that if the input is V here, and I represent it with this block diagram in here, I would have to multiply by 1 over R, and the output becomes I. See? This is in here, input, and this is the output. These words can be changed. You know, you could say this is the action, this is the reaction. Or this gets into a technical term. Why don't we call it the causal effect? Who causes causal effect? Or let's look at this term called causality. Causality, like this. So the idea of representing either this way or this way depends on what? Huh?
What variables you have?
Take a look here. What makes me do this block diagram, and what makes me do this one? The equation. This is the important conclusion. In fact, I am going to write it down in here so you can have in here. I'll just write it down exactly like that. This is the equation determines which block diagram I use. And I would say based on this concept of causality. And causality is the idea of determining which variable is the input and which variable is the output. Very good. Okay, this is as far as I want to go with a block diagram. But now I would like to address the bond graph approach. And so in this, we're going to use both of these. In here we still have the idea that we have this equation where the voltage is the result of the calculation of the current times the times R. Yeah, this physical law. It doesn't matter which method you use, you have to perform this, because otherwise we would be representing and discovering something different. That cannot be. All methods of simulation and all systems, some ways of representing a system, are based on the laws of physics. And Ohm's law is one of those, in this case. I'll just write it down so you remember. This is Ohm's law. Yeah. Now, what's this idea of bond graphs? This is another way of writing the same information. But in this case, I am going to say, let's see, let's draw a line in here. Just gonna say in here, on one side we have, let's say, the input in this case was I, right? On this side. And the output on this side was voltage like that, right? So, just the same idea. So, what we're going to do is we're going to find a way to represent this by classifying this element. This element is a resistive element, it's a resistor. Okay? So, in bond graph notation, we have we recognize the elements in here where, hold on for a second, I need to make a small correction here so that there's the space for us. This is the way we represent is by the element itself, this R element. Okay. What is the output in this case? Is this voltage V. And the way we write it is using this symbol. Sorry, I thought I needed the space, but I don't. I'll put it back where it was. This was the input, right? And this is the output. So I'm just going to write it down in a little different way here. Say this is input and this is the output. So now the input is represented by this line, see? And the output is represented by this crossbar. And this is as if you put your hand in here, just imagine yourself, hold this line with your left hand. Just hold it, do you feel it? Yeah, you hold it there. Holding it hard? All right. Push it to the right. And just imagine this is just like a piston. It looks like that. In other words, this sign in here gives you the idea that you can push with it, right? So if you hold it here, push it to the right, what you're pushing is the upward, is this V. And this symbol actually represents the same thing as this one. But also, this causal form, remember this is based on the concept of causality, which we introduced about 5 minutes ago. This causal form means that the voltage is the output and the input is this. Okay? This has the total equivalence of this block diagram. This bond graph that I just showed you here is exactly the same thing as this, because it represents the same equation. I just found a little different notation on how to do it. But seeing here, this is based, like I said, is equivalent to this. So you may say this format, I think sometimes it's good to put some lines that indicate these are equivalent. Hmm? But you see, we still have this guy. How do we do this one? All right? We still have to deal with the input and the output, same thing. So what we're going to do is we will draw it here the same way. This is now this one, yeah? They are elementing here. Now, which is the output in here? Let's do it together, because if you do it with me, I think you will have more out of this. What is the output here? I. So I'm just going to say the output in this case is, I'm just going to put this I as the side of the output here. What is the input? The E, right? The input would be the voltage. But now if we reverse this, the way we drew things, you see, instead of pushing it to the right, we're going to push it to the left. And this would be V. So now, imagine yourself holding this C, hold it with your little fingers here. I'm going to draw your hand in there. There you go. You're holding it hard. If you push it to the left, you are putting into the element. And this is the output, and this is the input. This one is completely equivalent. I mean, when I say equivalent, I mean equivalent to the equation here, for this one up here. This one is equivalent to this equation, and most certainly this is equivalent to this block diagram. So what has happened is, basically in shorthand, we have written the same thing. And so this is your block diagram here of this equation, and this is your bond graph of the same thing. This one is the block diagram of this equation, and this on the right hand side is your bond graph of the very same thing. So this symbol was invented precisely to represent this idea of the cause and effect, or the input and the output. But nevertheless, the form of this causal mark, this is called also a causal mark. You know, in bond graph notation, it's called a causal mark. This is the idea is that this causal mark would be either on the output, you know, is out of the element, or the causal mark is into the element. Either is the output or is the input. What I would do is, let me make a summary on what I just said in here. And I'm going to generalize this. I'm going to say, if you have element in here that this is A, and you have, you see, the other one, because the output and input happens on between two elements, you know, in this case the input and of course the output. If this is B, let's say, if you go from here to here with in this case, if the input from A to B is I, then it follows that the output from B to A has to be B. On this side, this one, if the input to this, you know, if I goes this way, this B goes this way. This is A and this is B. This one here it's typical of where if I comes in, B comes out, would be like this. And if this B comes in and I goes out, so this is I like this, B like this. See? So there is a complete equivalence of the two methods based on this principle that I just showed you. Both of them are based on the physical law of the system. But one we represented with block diagrams within Simulink here, and one we represented with bond graphs like this. So this kind of notation we use with Simulink. You know, for this is the Simulink notation. But this notation, CAMG understands this. But the idea is to be able to end up in the same place, whether we represent it using these block diagrams or using these bond graphs. We still would like to do the simulations of systems, just like we have done with the block diagram. So that is the short explanation of the equivalence in between those two.